Okay. 3D world, 2D method of analysis. Okay. So I'll keep the small diagram on the side so you can see. So the first thing I'm going to do, okay, always follow this procedure. I cannot highlight enough, okay. So we're going to view the structure in different orientation, okay. So now I'm going to view this and we're going to apply the 3 rules, okay. So we have our, I'm going to draw based on this transformation now. Okay. So this is my X and this is my Y. Okay. So we are going to draw the structure based on that orientation. Okay. So we will have our structure now. Okay. So we have for where I'm trying to make it to scale. Okay. And then we have our 10. Okay, so this is how our structure will look like. Okay, this is just a sketch. Okay. So the first thing we have to identify is we have to draw the element. Okay, so I'm going to draw the element. So our element, one is here and one is over here. Okay. So this over here is our element H. Over here, this is our element K. Okay. Then the next thing is we are going to draw our forces. So we're going to use vectors, okay? So that we have a force, right? So where is our eyes now? So basically we are viewing it, our eyes are here. Okay, there's our eyelash. Okay, this is our eye. We are viewing from there. So we know that we are looking at the tail end of the arrow, which is a cross, right? So this is 50 pounds. Then we have another tail end of the arrow. This is at 150 pounds. And then we have one force over there at 150 pounds. And then we have a dot coming towards us that is 200 pounds. Okay. So that's the forces associated with this structure. So based on rule number 2, right? Rule number 2 states that we have to immediately identify the position of the neutral axis. Okay. So the neutral axis is relative to the element. Okay. So I'm going to draw the neutral axis. So it's exactly at the center down here, at the neutral axis. Okay. So this is our neutral axis. Then rule number 3 states that do not analyze the cross and the dots. Okay. So the 150 for now, don't analyze. The 50 for now, do not analyze. The 200 pounds, don't analyze at all. Okay. So the only force component that we analyze is the 150. The you can see it's not a dot nor a cross, it's just a straightforward arrow. Okay. So Now we are going to focus on 150. Okay. So if you look at 150 relative to the neutral axis, okay. So then that's why I say the neutral axis is ever so important. You have to identify the neutral axis. So we know that you have a distance over here. You have a perpendicular distance over here. Then this perpendicular distance is 10 inches. Right? With 10 inches. And then you have to see if you have that component over there with the 10 inches, how will the structure deform? Right? So we are going to sketch the structure deformation. So the structure will deform this way. So this is the 150 pounds. So when it's deforming this way, right, it looks like a sad face or a smiling face, right? So this 150 will induce a what? Induce a bending moment. Okay. Then some of you might say, right, isn't it curious, right? You will ask me, Eugene, why this section is straight, right? Whereas this section over here is what? Bent. Can anyone tell me why? I'm not drawing this because that is the way I like to draw it. No, it's a fact when you bend it, it's going to look like that. Any idea why, anyone? Aren't you curious now?
Maybe because there is a fixed support.
Hey?
Fixed support on the left side?
Yeah, you are absolutely right. Okay, you're absolutely right. Because this point that I'm circling now, right? It has freedom of movement, yes or no? Right? So that is why this section over here is straight. At this point is where you have your what? Resistance. That's why it will bend. So if you have a structure like this, you bend it this way, right? The vertical component, which right, is always straight. Okay, it's not that I'm going to draw it this way. No, okay, you have to realize that. Okay, right. So now we are going to calculate the moment. Okay. So the moment, and if this is our if that's our this is our rotation in Z, right? So we know that our moment is in the Z direction. Okay, so the moment in the Z direction is equal to 150 multiplied by 10. So this is equal to 1,500 pound inch, right? And the moment vector will go this way. Okay, so the moment, okay, will go this way, right? So this is our moment in Z. Okay, like how I told you again, this is going to be compression. This is going to be tensile. So immediately you write this out. Immediately you put a square bracket. But before I go there, it's important to know what is your direction. Okay, this is moment Z. Why? Because now you can apply stress X is equal. Now stress X has components. Okay, it has the axial plus by mz over izz multiplied by y plus by my over iyy multiplied by z. Okay. Now this is critical because not always izz is equal to iyy. Okay. So for this case, we know that we only have mz, so we only have this component over here. Okay, we only have this component for now, right? But it's contributing to the what? normal stress in the x direction. Okay. So for this case, what do we know? Okay, by looking at the moment vector over here, right? You have to write this out because this will help you. Okay, we know that element H. I'll do in red. Okay, we know that element H is going to be in tension. Element K will be equal to what? 0. Right? Element H will be tension because it's above the neutral axis. Element K will be equal to 0. Why? Because it's at the what? At the neutral axis. That is why this course or this topic has a lot of what? Analysis. Okay. So we are not over yet. Okay. We are not over yet. So if you look at this 150 over here, right? The 150 will also induce an axial loading. Okay, so you have to translate the 150 down here. Okay, you have to, so there's another, you have to bring down the 150 down here. I need a ticker. You have to bring down the 150 down here. This is 150 pounds. Okay, and this, you have to shift it down to the neutral axis because it's going to induce a bending moment and an axial load. Now, some of you say, Eugene, we did not learn this. You did learn this before. Why do I say that you did learn this before? I will show you now. Right? Why is there a shift of 150? Right? Remember we did this problem? Remember we did this problem? We did this problem or this example. Right? And then the load, right? We have a load down here that's acting at 150. Right? And point C is the point of interest. And we have a distance over here known as D. Right? So what was our reaction, right? So we know that this will generate a moment, right? And this moment will be equal to 150 multiplied by D, right? So 150 multiplied by D. What else? Can you remember? Then we also have to incorporate opposite load down here. Oh, this is just too close. Stupid me. So this is 150 multiplied by D. And then we have to correspond with an axial load of 150. Yes or no? Right. This is exactly the same. Right? You have seen this before. It's just a matter of recalling. Right? So you have seen this before. It's not that you have not seen it before. Okay? Okay, so that's why we have to shift the load 150 over here. So from here, we know that we're going to have a px. We know that we are going to have px, and px is equal to 150 pounds, right? And then it will contribute in stress in the x direction, as in it's going to be 150 divided by your area. Okay. Now, if you were to look back in element H and element K, so immediately once you write this out, you have to, as I said, the practice that I will always encourage, you put a bracket down here. Element H, because axial load, will be doing a tensile or tension. Now, element K will also, you'll see a tension, right? Because it's axial loading. Let me make sure this is the same.